Hi class, this is section 5.4. Our key topic is factoring, and we've already done that, so this is about reviewing how to factor. Reviewing how to factor and going a bit further. So we're going to review a little bit what we've already studied for factoring, and then we're going to find another pattern as well. So in chapter 4, we did factoring, so we're going to start with that right here under our chapter 4 factoring review. So this first one, 9x squared minus 1, this should look familiar. This one's the difference of two squares. And we talked about this quite a bit in chapter 4. 9x squared we can break up into 3x times 3x. And negative 1 we can break up into 1 times negative 1. So this will factor into 3x minus 1 times the quantity 3x plus 1. And we talked about this one quite a bit. The second one here, this is a perfect square trinomial. And we also talked quite a bit about this one when we were working with completing the square. So x squared, we can break that into x times x. 16 breaks into 4 times 4. And if you do 4 times x and double it, you get our 8x, which is the pattern that we should have. So this factors into x plus 4, the quantity squared. Or you could say x plus 4 times x plus 4. This next one, there's only two terms, but they're not perfect squares, so I'm going to look for a GCF. And I notice that both 4 and x go into both terms. So if I take a 4x out of both terms, I'm left with 2x in the first term plus 5 in the second term. And my third one, I don't see any GCFs, and there's no perfect squares, so we're going to use the snip method on this one. And I should have written above, this one above was where we had a GCF, that was that pattern. So we're going to use the snip method here, and we have to think what multiplies to give us AC. So A times C here is negative 40, but it has to add up to B, and B in this case is negative 3. So factors of 40 that I can think of when I make one opposite will have a difference of 3 or 5 times 8. So I'm going to make my 5 positive and my 8 negative. The second part of the snip method is then taking both of our two factors and dividing them by a with our x. So I'm dividing them both by a, which is 2, with an x with it. So I'm dividing them both by 2x. Then we need to reduce these. Okay, so I'm going to just change the color quick here. If I reduce this, my second one, 2 goes into both, so it becomes negative 4 over x. And my first one, this is already reduced. Nothing goes into both 2 and 5. So this factors into 2x plus 5, that quantity, times the quantity x minus 4. And if you went through and used FOIL to double check to make sure it's right, you would find that that is indeed correct. So the second column is called grouping to factor. So what we're going to do is we're going to group pairs of terms that have a common monomial factor. So they have one common thing. So I'm going to group my first two here, and I'm going to group my last two here. I'm putting grouping symbols in. And the first two share an x squared, so I'm going to take x squared out of the first set of parentheses, and if I take x squared out, I'm left with an x minus 3. Now, the second group, I need to take something out, but I still need to have x minus 3 in the second set of parentheses. So you have to think, what can I take out of negative 16x that will leave me with a positive x? Well, I can take negative 16 out. And if I think of negative 16 times negative 3, there should be a negative 3 right there. Negative 16 times negative 3 is indeed positive 48. So the way we put these two together is we've got x squared minus 16. That's one of my terms, or one of my binomials. And the other is x minus 3. So this factors into the quantity x squared minus 16 times the quantity x minus 3. Now I notice though that x squared minus 16, x squared and 16, they're both perfect squares. That's the difference of two squares. So we need to factor this one step further. It would factor into x minus 4 times x plus 4 times the quantity x minus 3. So that would be factored all the way. This is my final factored form right here. It's completely factored. We always have to make sure we're completely factoring these. So my second problem here, I want to factor. So again, I'm going to add my grouping symbols in here. I'm going to group the first two and the last two. And I notice with the first two, they both share an x squared. So I'm going to take x squared outside of my parentheses. That'll leave me with an x in the first term plus 7 in the second term. So the second group, I want to take something out that leaves me with x plus 7. And if I notice from negative 9x, I can take out a negative 9. Negative 9 times x is negative 9x. Negative 9 times positive 7 is indeed negative 63. So I can now know that one of my factors is x plus 7, because I have that written twice. The other is going to be x squared minus 9. I need to make sure this is factored completely. And that x squared minus 9, those are both perfect squares. So that's the difference of two squares. I can factor this a little bit further. I can make it x minus 3 times the quantity x plus 3 times the quantity x plus 7. And there is my final factored form, factored as far as I possibly can factor it. Okay, this last one, I'm going to factor this again. So I'm going to add my grouping symbols around the first two and around the last two. We always put them that way. The first two share a 17x squared, so I can take that out of parentheses. And if I take 17x squared out of my first term, I'm left with a plain x. 17x squared out of my second term leaves me with a plus 2. So I know my second terms, I need to take something out that will leave me with x plus 2. And the value that I can take out is negative 9. And I know that because negative 9 times x is negative 9x. Negative 9 times a positive 2 is negative 18. So I'll now put these together. I know one of my terms is x plus 2 because that's the term that's repeated twice. My other term is going to be my 17x squared minus 9. Now we'll double check to make sure we're simplified all the way. 17, that's not a perfect square. There's nothing I can take out of 17x squared minus 9. There's nothing I can take out of x plus 2. So this indeed is my final factored form. All right, let's look at our last column here. These are special factoring patterns. So these are patterns that you need to look for, and once you see them, we're going to follow this pattern. So if I have two terms, my first term is a cube, and my last term is a cube. And they may not always look like cubes. You kind of have to test it and see if they are or not. So if I have a cubed plus b cubed, so I have two cubes termed and added, or two terms cubed and added, I can simplify that into a plus b, that quantity, times the quantity a squared minus ab plus b squared. And if I have the difference, so a cubed minus b cubed, that can factor into a minus b times the quantity a squared plus ab plus b squared. So these are just special patterns that you need to learn to look for. So for this first term, it says factor x to the third plus 64. Well, x to the third, well, I know that's a cube, so a here is x, and 64, that's actually 4 to the third power. So since that's 4 to the third, b is 4 here. because I could write that x to the third plus 4 to the third. So a is x and b is 4. So let's follow our pattern. Since they're added, we're going to follow the top pattern. So this becomes x minus 4, not x minus 4, x plus 4, times the quantity, a squared, a is x, so x squared, minus a times b, so 4 times x, so minus 4x, plus b squared, and b squared, that's 4 squared, so plus 16. I can't do any simplifying further, so it's x plus 4, that quantity, times the quantity x squared, minus 4x plus 16, and this is my final factored form. For my next problem here, factor 8 times x to the third minus 125. So really, I know that 8 is 2 to the third power. So really, I have 2x to the third power minus 125 is 5 to the third power. So these are just patterns or numbers that you need to look for. So it's minus 5 to the third power. So my a is 2x and my b is 5. So I'm going to follow the second pattern because the second pattern is a to the third minus b to the third. So following the second pattern here, it's going to be a minus b, so a is 2x, b is 5, so it's 2x minus 5, times the quantity. Now I have a squared, so 2x squared, and then I have a plus a times b. A is 2x times b is 5, plus b squared, so b is 5, and I have that squared. So now I need to do a little simplifying. This is 2x minus 5, that quantity, times the quantity. 2 squared is 4, x squared, plus 2 times 5 is 10x, plus 5 squared is 25. So here's my simplified form. The last one, I want to factor 16z to the fifth minus 250z squared. Now right away I notice both of those terms have a z squared in them, and both of them are also even. So I can take a GCF out. I can take 2z squared out of both of those, and it'll make it much easier to work with. So this is really 2z squared times the quantity, 8z to the third. Now 8 is 2 to the third, and then z to the third, so really my a is 2z there, minus 250 divided by 2 is 125, and I took the z squared out here. So really in this case, my a right here is 2z, and my b is 5, and they're subtracted, so I'm going to follow the second pattern. So to factor this, I need to keep my 2z squared on the outside. I need to keep that right there. I'm using the second pattern, so it's a to the third minus b to the third. So it's, first of all, a minus b, so it's 2z minus 5 times the quantity. I need a squared, so I have 2z, that quantity squared, plus a times b, so that's 2z times 5, plus b squared, so that's 5 squared. Now we need to simplify this, so I still have that 2z squared hanging out in the front. 2x minus 5 doesn't, or 2z minus 5 doesn't simplify, so I'm just keep it 2z minus 5. And then I have the quantity 2 squared, which is 4, and I still have z squared, plus 2 times 5 is 10z, plus 5 squared is 25. So there's my final answer right here. That's a lot of factoring, but we're going to actually use this to help us solve polynomials. So let's flip over your frame and look at the next side. Okay, so now we're going to be solving polynomial equations. Our first step is going to be to set our equation equal to 0. Our second step will be to factor the polynomial completely. And then the third step will be to find each value of x. So first we want to set our equation equal to 0, so I need to move my 18x to the third to the other side by subtracting it. So then this side will cancel out. So I need to put this in the right order. So the correct order will be 3x to the fifth minus 18x to the third plus 15x equals 0. So I just made sure I put that in the correct order from highest exponent to lowest exponent. And one thing I noticed right away is that 3x goes into all of those terms. So I'm going to take out a GCF. So I'm going to take 3x out of all my terms, and in my first term that will leave me with x to the fourth, minus my second term that'll leave me with 6x squared, plus my third term that will leave me with 5. And this equals 0 still. Now we notice, if you look here, x to the fourth, the number in front of it, there really isn't an a there, so we can factor this actually pretty quick and easy. Even though it's x to the fourth and not x squared, we can still think, well, x to the fourth is x squared. That's x squared times x squared, and we can think, what can multiply to give us positive 5? That adds up to negative 6. Well, if I split that up, it'd be negative 1 times negative 5. So this actually factors into 3x times the quantity x squared minus 1 times the quantity x squared minus 5. And that equals 0. Now, I also notice here, x squared minus 1, this is a perfect square. So I can still simplify a little bit further. So this really is 3x times the quantity x plus 1 times the quantity x minus 1 times the quantity x squared minus 5. And that equals 0. So I'm trying to solve this now. I want to find each value of x, the value that would make each one 0. So I can take each of these pieces and set them equal to 0. So I can say 3x equals 0, x plus 1 equals 0, x minus 1 equals 0, and then also the final piece, x squared minus 5 equals 0. So for 3x equals 0, if I divide them both by 3, I have x equals 0. It's one of my solutions. So my solutions, I'm going to write them right down here. My solutions are x equals 0. This next one, if I subtract 1 from both sides, I have x equals negative 1. So x equals negative 1. This third one, if I add 1 to both, I have x equals positive 1. So x equals positive 1 is a solution. And then this last one, if I add 5 to both, I have x squared equals 5. And then I'll take the square root of both sides. So x equals positive or negative square root of 5. We can't reduce that any. So my final two answers are x equals the square root of 5 and x equals the opposite, or the negative square root of 5. Now I want you to notice here how many solutions there are. There's 1, 2, 3, 4, 5 solutions. Okay, so we've got 5 solutions in total here. And look at our equation. Let's see if we find a pattern here. 5 solutions for an equation that looks like this. And when we did quadratics last chapter, we would have an x squared, and we would have 2 solutions. So look right here and think, I wonder how many solutions we're going to have. So take a guess at that, and let's see if you're right here. So this is already set equal to 0. Our first step is already done for us. We want to factor it completely, and I right off notice that 4x goes into all the terms. So I'm going to take 4x out of all 3 of my terms. So if I take 4x out of all the terms, I'm left with x to the 4th minus 10x squared plus 9. And this is just like the previous one, where even though the first one's x to the 4th, I can think of that as x squared times x squared. And I can think, what can multiply to give me 9 that adds up to negative 10? Well, that'd be negative 9 and negative 1. So this really factors into 4x times the quantity x squared minus 9 times the quantity x squared minus 1 equals 0. And I notice right away x squared minus 9, perfect squares, so it's a difference of 2 squares. X squared minus 1, both perfect squares, so that's also the difference of 2 squares. So this factors into 4x. Let's split our x squared minus 9 up. That's x plus 3 times x minus 3. And then x squared minus 1 becomes x plus 1 times the quantity x minus 1. And we want to find all our zeros for each of these ones. So I can say 4x equals 0, x plus 3 equals 0, x minus 3 equals 0, x plus 1 equals 0, and x minus 1 equals 0. So I factor everything, now I'm just solving them. For the first one, 4x equals 0. If I divide them both by 4, I have x equals 0. Second one, x plus 3 equals 0. Subtract 3 from both. I have x equals negative 3. For the third one, add 3 to both. I have x equals 3. For the fourth, subtract 1 from both. X equals negative 1. And for the last one, if I add 1 to both, x equals 1. So my solutions are x equals 0, x equals negative 3, x equals positive 3, x equals negative 1, and x equals positive 1. And notice there are 5 solutions, and that's because the degree of this polynomial is 5. Okay, so 5 solutions because of the degree. Make sure you make a note of that. We'll make a note right here. 5 solutions. If I can spell the word solutions right. 5 solutions because the degree is 5. So if I have a second degree polynomial, I often have 2 solutions. This last one, I want to solve this one as well. First step is not done yet because it is not set equal to 0, so I'm going to subtract 14x to the third from both sides. So, putting this in standard form, it's 2x to the 5th minus 14x to the third plus 24x equals 0. So I have now put it in the correct form. Looking at all those terms, I notice that 2x goes into all of them, so I'm going to take 2x out. That's my GCF. I'm left with x to the 4th minus 7x squared plus 12 equals 0. And again, even though the first one's x to the 4th, I can still think that's x squared times x squared. What can multiply to give me 12 that adds up to negative 7? Well, that's negative 4 and negative 3. So this factors into 2x times the quantity x squared minus 4. Oop, minus 4 is perfect square. It's a difference of 2 squares, so I'm going to have to simplify that more. Times the quantity x squared minus 3. Those aren't perfect squares, so that one will stay. So I have my final factored form is 2x times x plus 2 times x minus 2 times the quantity, oops, that should be x squared minus 3 equals 0. So finding my solutions. The last step here, right over on the side here. So I can say 2x equals 0, x plus 2 equals 0, x minus 2 equals 0, or x squared minus 3 equals 0. So my first solution for 2x equals 0, that means x equals 0. My second, if I subtract 2, x equals negative 2. My third, if I add 2, x equals positive 2. My fourth one, if I add 3 to both sides, I have x squared equals 3. I then need to take the square root, so I have x equals positive or negative square root of 3. So my final solutions are x equals 0, x equals negative 2, x equals positive 2, x equals the square root of 3, and x equals the negative square root of 3. And those are my 5 solutions. This is a 5th degree polynomial, so that's exactly what I would expect to have, our 5 solutions. So this is the end of the frames for lesson 5.4. Please make sure if there's anything that didn't make sense, you star it so we can talk about it in class tomorrow, and have a great night.